So far we've used the derivative mainly as the slope of a tangent line, right? We've derivative equals slope, slope equals derivative, and we've done a lot of tangent lines. Instead of having change in y over change in x, though, we might do something a little bit different and do change in position over change in time. This is kind of physics, right? Change in s over change in t, that would be like velocity. An example would be if we went 300 miles in 6 hours. That's pretty easy. You'd say the velocity is 50 miles per hour, right? 300 divided by 6. In fact, units become really important in this section. And you'll be able to answer some questions. You've probably figured this out in physics and in chemistry. Like if you can make the units work, you don't always have to understand exactly what's going on in the problem. You figure that out in physics and chemistry. Like, hey, make the units work. You can figure out the formula without really knowing what's happening. 300 miles divided by 6 hours, well, that would get me miles per hour. It's like, yeah, that's like week 1 of physics right there. That's a velocity, a speed, a rate. Rate's another good word for derivative. If we do a limit process, we could have an instantaneous rate of change. So remember, instantaneous rate of change, that's the speedometer. That's what the speedometer tells you. How fast are you going at this moment? When you get to the end of the trip, then you can say, well, my average velocity was 50, and you were probably going 50 for some of the trip, but some of the trip you were probably going 60, and some of you were going 40, and maybe you hit a stop sign or whatever. So you had different instantaneous rates of change, even though your overall rate of change, your average rate of change, was 50. What we're going to be looking at is instantaneous, right? Because the 50 is algebra, like you've already done that. We just want to tie that to instantaneous, and that's what we're going to do. So first we have to get comfortable with the notation. To get an instantaneous rate of change, we're taking a derivative with respect to time. So that usually means dt is in the bottom, like change in time. So job 1 is, let's try to translate a few sentences into calculus notation. The area of a circle is increasing at a rate of 6 square inches per minute. So the area of a circle is increasing. So I'm not going to say A equals because it's a rate. So it's not A equals, it's dA dt equals because something's changing. And the rate is 6 square inches per minute. Inches squared per minute. So the units still line up here. A change in area would be inches squared. A change in time would be minutes. The volume of a cone is decreasing at a rate. So don't write V equals. This is a rate problem. So dV dt. The volume is changing at a rate of 2 cubic feet per second. And that's not quite right. You know what's not right about that? I snuck in an important word that's different in number 2 than from number 1. It's decreasing. So how is its volume changing? Well, it's negative because it's decreasing. Why don't you try the next 3? So all you're doing is writing a little calculus equation based on what they tell you. You're not even doing anything with it. Just try to put in notation what they put in words. So there's the 3 that we didn't do. 3 people per day is dP dt if you want to use population. Height of a tree, dH dt, is half a foot per year. Again, you can make sure the units match up. Height is in feet, time is in years. The height or level in the fish tank is decreasing, again a decreasing, at a rate of 2 inches per hour. height per time, inches per hour. So the first part of working these problems, we're not even working the problems yet, is understanding the information that they give you and putting it into a calculus type notation. All right, the second set is kind of the same thing, just in reverse. So if you give you each of the following, write the sentence correctly, describes the relationship. Try to include the word rate in your sentence. Rate is kind of the giveaway that you're dealing with a derivative. Derivative, slope, rate, all those go together. So inches per day, dc dt. I don't know what C could stand for. Capital C, anybody? What's a math word that starts with C? Circumference. Let's go circumference. So let's say the circumference increases at a rate of 2 inches per day. And we'll how about capital S for number 7 here? Especially if it goes to yards squared. So what would have a unit of yards squared that starts with S? What's that? Surface area. We don't know that it's surface area. You could just make up something. It would have to be area, though, because that's what the units are. So, and we don't have to make an official sentence. We're just working on our calculus, English to calculus translations here. So surface area, it's positive, so increases rate of, I'm just going to get really sloppy on my English here, 5 yards squared per day. Nope, whoops, yep, got to read, careful here. Yards squared per minute. The last one was per day, this one's per minute. Try the next two. You don't need to do the last one. That's enough examples. Try the next two. All right, so there's the last two. The area decreases at a rate of 4 feet squared per second. And radius, I guess you could have said something else. It's not guaranteed to be radius. The ruler, I don't know. Radius increases at a rate of 40 centimeters per minute. So I don't think that's too hard, but that is new. Translating rate statements into notation and notation into rate statements. Usually you're doing 1 through 5. That's, I don't say it's more important. You got to be able to do both. But 1 through 5 is usually the problem statement. And so you got to know what they're telling you before you can work the problem. All right, a little note down here at the bottom. The units will be very important in this section. Tried to highlight that already. Units are super important. And from now on, when I refer to a rate of change, you should automatically assume that it's an instantaneous rate of change. In other words, it's a derivative. Okay, we tested this on the last test, instantaneous versus average. And I was pretty clear to say instantaneous or average. I said both of those things on that test. From now on, because most of what we'll do is instantaneous, because that's calculus, and average is just algebra, if we say rate of change, we mean instantaneous rate of change. If we mean average, we have to say average. So generally speaking, we'll be doing calculus in here. Occasionally, we'll sneak in an algebra problem. So you can set your brain to calculus and just know that if average shows up, that's an algebra problem. All right. Page 2. Now we start taking derivatives. Next thing we have to learn is to take derivatives with respect to time. Usually we're taking derivatives with respect to x. Right? D dx is almost exclusively what we've done so far. think almost exclusively, or just plain exclusively. I think that's all we've done so far. Now we're going to take them with respect to time. I guess the good news is all the rules are the same. It's just now we're looking at t versus looking at x. For each of the following formulas, identify the formula and then take the derivative with respect to time. Man, this notes page I stole this from somebody, but they really outlined everything here. I will do the first 3 examples, and then you will do the others on your own. Identify the formula. Okay, well, that looks like the area of a circle. So that's just keeping up our, most of these are geometry things. We recognize our geometry formulas. More importantly, let's do the derivative of this thing. So derivative with respect to t to all of these. That's what we're doing. So dA dt equals, any guesses on the other side, knowing that the rules are still the same? Any thoughts? What's that? Say it again. I can't hear you. With the 2 times the radius, but pi is still there. So 2 pi r. That's mostly right. Mostly right. Because we want to consider that the radius is changing, or you think of it as a chain rule problem. So if what you're taking the derivative with respect to isn't the variable over there, you've got to include the dr dt, just like we had to include dy dx on the end of all those other things for implicit. So that's sort of the connection with implicit, is unless there's a t over there, which none of these have them, you're going to have an extra dr dt or dh dt or dv dt. So everything's going to have a dt in the bottom of it. All right, let's do number 2. What's that the volume of? What do you recognize what that equation is for? Pi r squared looks like a circle. So a cylinder, you got a circle times the height. There's your pi r squared times the height. So that's the volume of a cylinder. Now that one's got 2 variables in it, r squared and h. So we're going to have to use the product rule on this one. So dv dt. So I'll identify the pieces, but I'm going to do the product rule kind of in place here, just because I'm limited on space. So I'm going to say f is pi r squared and g is h. So first times derivative of the second would be pi r squared. Derivative of h isn't just 1, it's 1 times dh dt. Plus the other way around, h, so times the derivative of pi r squared. So that would be 2 pi r dr dt. Okay with that? So product rule combined with chain rule, taking a derivative with respect to time. There's a lot of stuff going on. And what this means, like if we can think practically what that says, is that a volume changes depends on if the height is changing and if the radius is changing. I mean, and that kind of makes sense, right? If you take a cylinder and you increase the height, you rate change the height, then you would change the volume. If you also change the radius, you would change the volume as well. And this equation kind of relates how all of those things might work together. Number 3, what's that look like? You recognize that one. Pythagorean Theorem. Right triangles. So with respect to t, derivative of a squared would be 2a, but then you got dA dt. oops, not equals, plus. Derivative of b squared would be 2b times the derivative of b, db dt, equals, on the other side, 2c dc dt. So step back from the details of using the power rule and chain rule, and what this means is, think about a triangle. If A and B are both growing, if A is changing and B is changing, well, then that would mean C is changing, right? If you increase the two legs of a right triangle, well, then C is going to get bigger. And this equation tells us how that would happen. Let me do number 4, and then I'll turn you loose to try some of these on your own. Will anybody recognize what that formula is for? S, we've seen S already, so surface area. 2 pi r squared, that's like 2 circles, plus some other stuff. 2 circles, plus some other stuff, so that's the surface area of a cylinder. You're not going to have to know most of these. You definitely won't have to know that one. Some of the basic stuff you'll have to know, but area of a circle, like easy stuff. So ds dt equals, I got another product rule situation here. So this has a product rule on 2 pi rh, and then I'll handle 2 pi r squared at the end. So first times derivative of the second, 2 pi r dh dt, plus the other way around. So h times derivative of 2 pi r. So derivative of r would just be 1. The 2 pi is still there, but then dr dt. And then careful, this one people forget because they get so focused on the product rule that they forget there's another piece out there. So plus 4 pi r, using the power rule, 4 pi r dr dt. That one's a little more complicated than the others. Why don't you try, let's see, 5, 6, 7, 8. You get a product rule in number 8. So try 5, 6, 7, and 8, and then we'll go over those. Okay, so there's 5 through 8. Thank you. Unfreeze the screen so you can see them, which means you couldn't see them when I was doing them. So check those. Questions on any of those? I'll give you a minute. That's a lot to process and check. Or check me, make sure I did them correct. Questions, comments, concerns? Are we good? Especially that last one, the product rule is tricky with these sometimes. Okay, well here's the assignment for today. Let's just finish the rest of these. So do 9 through 16. And if you need to do them on your own paper or spread them out, you can, or if you just want to write real small, I guess you could do that as well. So today's assignment, again, ignore what's on the calendar, I'll change it later. But today's assignment is just finish 9 through 16. And we'll go over those tomorrow. And because of that, we will definitely push the test back till Tuesday, because we need a few more days to get through everything on related rates. So there's a lot more coming to related rates, but this is a good place to stop. Kind of halfway through, make sure you understand all this, and then we'll actually work some problems with all this stuff tomorrow. So job today, 9 through 16. That's an easy assignment today, I think, I hope.